Is it in series or is it in parallel? Before you blow up that inverter, watch this video and learn how to connect your panels in parallel or in series. This is Mr. Saina, your pumping, solar and irrigation expert.
So welcome back. So we are going to select panels and we are going to configure the panels to suit our inverter. So right away, let's go and do the selection. In normal cases, they come in 160, 200, 250, 285, 300, 345, 450, 545, and many others. The objective is to get an optimum arrangement for the panels. And before we go to that level, we are going to see what is parallel and what is series combination. Okay, so in series combination, you connect the terminals, the positive to the negative, positive to the negative. So this is how we do it. Let me demonstrate. So you have your positive cable from the first panel. You join it to the negative terminal. It goes to the positive terminal. So you have a situation where, for this case, you have positive, negative, positive. For then you have the neutral, actually the negative. Then you have the negative terminal. That is it. Then positive terminal, and then finally negative. So in this situation, you can see that um, our panels have finally a positive and a negative terminal at the end, and we are going to connect them using uh, MC4 connectors. We are going to see how to connect them later in this tutorial. So um, let's go to the series, the parallel. So this is the parallel connection. This is your parallel connection. This is you connect all the positives. Parallel connection, you connect all the positives. You connect all the negatives in one. Okay. And finally, you have your terminals. We have situations where you combine. Um, you do a series combination. You do a series combination, and then you do another series combination, and then you do a parallel combination, so that you have a combination of series and parallel. This is how it goes. So you have your positive, then negative, positive, negative. Okay, and then your negative, your positive, your negative, and finally your positive. Then the same scenario you have like that. You have So you have an arrangement of a series, and then you have another arrangement in series. Then you combine this terminal and this, and then you combine this terminal and this. Then you have one terminal. So you use a combiner box. You use a combiner box to you to you will pick these terminals and put them in a combiner box, and you will need MC4 connectors so that you can be able to do this kind of connection. Um, this is the MC4 connections, These are your MC4 connectors. Okay, and this is the female side. This is the female side. This is the male. This is the male. So in this scenario, you are going to bring your male to the female. This is the male part. And then for this case, you are going to pick the female part. You connect it here, and you have, so finally you will have this terminal and this terminal getting into your combiner box. This is a combiner box. You can have a look. This is a combiner box. Okay, it's this is a combiner box. This is how it looks like. So this is what you use to combine the DC voltages. Now that we've known what series and parallel is, let's go back now to our panels. Okay, so let's look at this panel. This is a 200 watts panel. It has a VMP of 30 and a VOC of 36. As you can see, the current is 6.67. We have another panel. Let's see this one. This one is 300 watts. Let's see this one. This one is 200 watts. It has a VMP of 36.48 and a lower IMP of 5.48. Okay, and you can see it is still a 200 watts panel. So we don't use the ISC and the VOC to calculate the rated wattage of a panel. We use the IMP and the VMP. So it is this area that gives you the MPPT power, that is the maximum power of the panel. Okay, so now that we've understood, we are going to use, for our case, we want to use this panel for our sizing. So let's go to the next step where we now pick our inverter, and our inverter is a 2.2 kilowatts system. That is 2200 watts. So the first thing that we check is the maximum VDC input, and we can see a range of 150 to 450. So the maximum is 450. We need to take care so that we don't exceed this voltage, so that we don't exceed that voltage. We have to also confirm the MPPT range of the inverter, which is actually 150 to 450. From my experience, our system works well when it's operating at 330 volts. So we are going to use it as the optimum MPPT in our calculations. So the next other item that we need, so our MPPT range is 150 to 450 and operating at 330. So the next thing we look at is the output current and voltage. In this case, this system has an output of 14 amps. So this is very important when you are sizing your loads, so that you don't exceed this current. The other thing that you need to confirm is the output. Is it single phase or is it three phase? And if it's single phase, if it's out single phase, is it 220, 240? Is it 220 or 110? If it's three phase, is it 220 or 415? Those are some of the things that you really need to check. I remember in 2008, when I was in the industry, I blew up inverter because I didn't check the input voltage. It was an American inverter. It was 110 volts. I assumed it was 240, the British standard, and I bleed. So it's very, very important to confirm the output. Okay, so once you've established the parameters that needs to be put, we come to the next level where we now, so our system is our inverter is 2200 watts, We factor in some form of provision for losses in the system. Now, in our case, from my experience, we provide anything between 1.35 to 1.70. Remember, these are some cost implication. We'll see what those cost implications uh, can be. So for this case, I will be constrained by two items. That is the maximum VDC, which is 450. The other constraint will be optimum power, which will be given by our MPPT voltage. In this case, it's 330. So let's have the first constraint, and let's apply the first constraint, which is 450 divided by 450 divided by, let's see our how many volts. Our panel has that one. Our panel has 43.6 volts. Let's apply the constant divided by 43.6. So we have 450 divided by 43.6, which comes to 10.32. So in this case, we have 10.32. 10.32. So we cannot round off to 11, because if we round off, we will exceed 450. So it will be 10 panels. It will be 10 panels. So that is the first constraint. Let's come to the second constraint. In the second constraint, we are looking at 330 divided by this 330 divided by 6.48 is equals to 9 panels. So this constraint is giving us 9 panels. Okay, giving us 936.48 is giving us 9 panels. Let's go ahead. So we have two constraints. I have the constraint of the maximum VDC, so I cannot exceed 10 panels. For me to get the optimum actually, or the minimum, not the minimum, the optimum will be 9 panels. So let me introduce another constraint that is now this range. This will be between 2970 to 3740 watts. Okay. So I need anything between here, and my system will operate optimally. So I can decide to use a 9S2P. A 9S2P is 9 panels in series and two strings. So I connect 2 strings in parallel. Okay, so for our case, we will now have 9 panels. We will have 9 panels. So we are going to have, so in our situation, we are going to have 9. So 9 times 2. So this is how we are going to connect our panels, and we are going to have an optimum. So let's check. 18 times 200 is equals to 3600. In this case, we are going to achieve over 330 volts, and we are going also to ensure that our system operates at less than 450, less or equal to 450 VDC cost. Remember, our system can work at between it can work very well between 3,000 to even 3,600 for that case. So assuming you don't use these 600 watts times an average of, let's say, 50 shillings per watt, this is 30,000. So in this case, you can have one quotation which is lower by 30,000, but it doesn't mean that uh, whoever is quoting is is cheaper. It might mean that the system has not been optimized. And what are the consequences of not optimizing the system? Um, so the first consequence is effects of clouds and winter. The other problem is in situations where the climate is hot and the system operates close to close to the minimum voltage. So when the heat hits up the panels, the VOC drops. Then the VOC and VMP drops, and these can have consequences in the system. The system can shut down. And a very good example is those systems that work in the morning and in the evening, and they don't work in the afternoon. Those systems have a design problem related to VOC stroke VMP design. If you need any help in sizing your inverter, you can come to the comment section in my YouTube channel and I will assist you to size it. If you like this video, hit the like, subscribe, and the notification bell to receive more of these videos. This video is courtesy of Kalen East Africa, House of Pumps, Irrigation, and Solar Pumping.